Good evening and welcome everybody. My name is Obi-Wan Pez and this is N-Simplex Pachinko. We're doing some math tonight, so please let me know what kind of math anybody would like to see. Generally speaking, we do stuff at the collegiate level. Can discuss pretty much everything at my monitor is telling me that there's another ad break going on right now, but it told me that there was an ad break going on when I actually had an ad break going. I don't understand. Alright, anyway. Typically we do stuff at the collegiate level. Generally speaking, everything up through and including differential equations, linear algebra, and multivariate calculus. We can also discuss some stuff that goes beyond there. We'll see how it goes. So, yeah, and it's not even like the one that's attached to, it's not even the one that's attached to like my browser. It's the one that's attached to my monitor. It's like it's a different computer. That's the Obi-Wan Pez mod account. Like the account that I'm actually running things from here, it works fine. I don't understand. Yeah. So I instead of like shunting one of my PCs off or trying to sell it to somebody, which believe me, it would not have gone terribly well because this thing is at this point that PC is probably about 10 years old. Some individual parts might only be 5, but that one's 10. And then this one I just built from scratch, and I told my spouse, all right, so I'm looking for like making an entire system from scratch, and she was like, all right, just not ridiculous. And I was like, you're gonna have to define ridiculous for me. And a real good evening. Yeah, and I'm wondering if I should probably, like you and Don do, start and I don't know, like it seems like everybody's trying it. Might be a good idea, but at the same time. But also, like, this computer, I'm not sure it can actually handle anything anymore. Yeah, Zach, I just didn't get rid of the old one. That's why I have a second PC. It's not that I was planning it. But yeah, since I left my job in the States and came here, I no longer have an Adobe account. So that means I'm going to have to do DaVinci Resolve or something like that. And so far, I've been having a really rough time trying to get DaVinci to work on my Linux PC. So I don't know. I missed it by like this much, because if I had just done it a few, I think, weeks earlier, it wouldn't have updated all of these like individual things that it depends on. And now it's just completely screwed. OBS plugin, yep. Yeah, pay the Adobe gods. Yeah. If I were making back the same amount of money-ish, then I probably would be happy to pay those licensing fees. But at the same time, like, it was a lot of money. $60 a month. Oh. I mean, no, well, like, why not both, right? The interface was awkward. That's also fair. Alrighty. Anybody have any ideas what they would like to see tonight? We could possibly attempt tensor calc again, but oh man, I'm gonna need some serious time and possibly a coach for that one. Collatz? Yeah, there's no way to actually solve the Collatz conjecture, but hey, sure. Jed? Sure thing. Now the next question is, do you want Euclid or do you want Jacobs? Andrew, absolutely. We can try it. An effort not to knock the sewing kit on the floor and spill all of its contents. We will shift stuff around first. Jacobs definitely has the prettier pictures. Euclid has possibly the more mathematical pictures. Yeah, we can give Markov chains a shot. 3 coins with bias for heads P, okay. Determine the likelihood of the following. Cool. And anything that has to do with, like, binomial, this is probably the right channel for it. As much as I don't want to, like, you know, claim that, I mean, I'm certainly not the best, but of all of us here, I probably have more experience playing with the number part of it, not necessarily doing the individual problems, but... Have I looked at trinomial expansion? Or has Andrew looked at trinomial expansion? Yeah, so if they're equal to each other, that's not actually too bad. Okay, so heads being greater than or equal to 2 is success. Okay, if you get one head, do you then only throw the other 2? throw all 3 every time. So you get 1 freebie, which then means the only failure state in the next one is all 3 are tails. And one more time, are all 3 of their probabilities the same? Biased, but the same. Same bias, okay. 3 heads, bias, coins. Probability P to land on heads. Two or more is considered a success, and if 1 is thrown, the only failures can be 3 tails, which has a likelihood of 1/8. Nope, 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 nope. Biased. Alright, 1 minus P. There we go. Okay, so when we... Okay, sorry, I thought you meant if the throw count goes beyond 2, the extras are worthless. That's not what I meant, sorry. I thought that you meant... I thought that what you were saying was if you throw tails and you have 1 head, right? If you throw all 3 tails, you only get 1 next throw where it counts. But you're saying that that 1 head will just continue carrying on until you get more heads, and then it counts as a win? Okay. Hum hum hum. So yeah, I would think that the... Okay, doesn't reset until you get a win. Alright. So what we're seeing... is this line right here, being thrown over and over and over again. With likelihood, right, P, 1P cubed plus 3P squared 1 minus P plus 3P 1 minus P squared plus 1 minus P cubed. Right, these are automatic successes, which make it probability 1/2. Right, these are 4 possibilities out of 8. P plus 1 is going to be equal to 3/8, and then P of plus 0 is going to be 1/8. Okay. So we've got 3 possible outcomes. Cal Polypomona? Not sure I know that one. Okay, this is going to be a success state. Here, this is going to get us a plus 1 at a probability of 3/8. And then this is going to get us a plus 0 at a probability of 1/8. Right, and then at 3/8, we're going to have the same 3 things. Success with probability of 1/2, and then a plus 1, which also counts as a success at a probability of 3/8, and a plus 0, which doesn't do anything or damage it in any way. With a probability of 1/8. Okay. That. Ends up succeeding. So like all those. And then we're just going to keep repeating this. Okay. After getting a plus 0, success ends up being probability of 1/2. And then plus 1 and plus 0 are not successes, but then alright. Blech. Success at 1/2, or success at 3/8 going the other way. Success also at 1/2 here. And failure state at 1/8. Failure state at 1/8. That's not the same failure state. Damn. That's going to be a plus 1 at 3/8, and then a success at 1/2. Some of these get messy. Sorry. Hey Govan, how's it going? Yeah, I should probably do something about that and make an actual Discord command, but at the same time, since we're using pen centers. That's a good point, because here I was just doing the number of states, so that's not correct, because here you still need to talk about the I'm still trying to do Oy. Yeah, I'm still trying to do fair coins, so that doesn't work. Right, it's not the probability. That's not the probability of these states. It was a half of like the possibility space, but yes. So Govan, you can put that in Pen Center's math forum or maths chat if you want. Can go either way. That's fun. Laz was also doing a Markov chain or something problem. Oh, that's a cool problem. Too bad Penn already answered it. Maybe we can do that one later. Anyway. Or try a different one that's the same sort of thing. Alright, so the probability for successes here is going to be literally what I already wrote up here. So it was going to be so 1p cubed plus 3p squared times 1 minus p. Right, so that's our probability of just straight success. The probability of getting plus 1 is going to be 3p times 1 minus p squared. And the probability of not getting anything is going to be 1 minus p cubed. Okay. By thinking real hard. Honestly, I mean... So, the way that I'm seeing it, right, is that failure is going to be 1 times, nope. 1 times 3p 1 minus p squared plus some infinite number of, gonna love that, 1 minus p cubed. Alright, plus And that's in any order. Wherever that single one comes, or if it doesn't come at all. Right? So, oh, times. Jeez. I don't know if we can do times, because that's going to make it effectively 0. Right? For n throws, right? It's going to be, yeah, times. That's not times. Jeez. This thing raised the n. Plus, always getting y minus p cubed to the n plus 1. Yeah. So if you do it as an infinite sum, that failure will tend to 0. And so, therefore, it effectively becomes 0. Or we could do, I guess we could do -1 here. Because if we just want n flips, right? Clean it up a little bit. So that means that failure is going to be p to the n times 3p y minus p plus, nope, that's not it at all. Oy. Okay, that's 3n minus 3. That'd be 3n minus 1. Okay. And then plus 1 minus p to the 3n. I don't know how helpful this is going to be, but so in doing Markov chains, hey, how's it going? Good evening, Alec. Welcome on in. Alright, so if we set this up as a Markov chain, this is going to have probabilities using linear algebra. Right? Okay. Yeah, yep. So, if we're in each individual state, how do we get to every other individual state? So, if we had... That was what we were trying to do with the tree up here. I erased it. Yay! So if we go from null right? Never flipped a coin. Or we have gotten a point, right? So we go back to null. And we can go to success state with a probability of 1 times p cubed plus 3p squared 1 minus p. And then success back to null is just 1. Because you always end up just going back. Null can also go to prime, like you said, at a probability of 3p times 1 minus p squared. And null can go to itself at a probability of 1 minus p cubed. Prime goes to success at the same probability that we had, well actually, any of the 3 probabilities above. So p cubed plus 3p squared 1 minus p plus 3p times 1 minus p squared. And prime stays itself at a yeah, that's fine. Prime goes to itself at a rate of 1 minus p all cubed. So I think that's how you want to do that. Prime will then go back to a null state at a probability of 0. You said it'll never go back. And success goes to itself at a rate of 0. Right, it just goes back to null. So I think that that would set up your, and success also goes to prime at a rate of null. Okay. So I think if you use that diagram, yeah, you should be able to set up a, in this case, 3x3 matrix, which then you multiply by itself over and over and over again, and see what the final state is going to be. Might be a slight nightmare with all of that. But you might be able to find some sort of sum. In fact, you could probably just shorten all this to like P1, P2, P3 and see what happens from there. But there might also be a slightly better way to organize this. If anybody else in chat has any insights into how this might be better managed, go for it. But I think you're going to find like a certain... This actually shouldn't be awful, question mark. You might be able to do it. If p is a prime greater than 4, says Govan, prove that p has the form 4kr, where r is either 1 or 3. Okay. Oh, 4k plus r. There we go. So what we're looking at is really modulus. Right, so either this is going to be mod 1 or 3, sorry, 1 or 3 mod 4 You have a proof of temp for part A, and part B got pretty much stuck. That's fair. Yep, okay. I completely agree with you there. Yep, 4K is not prime. Agreed. 4K plus 2 has to be even, so it can't be prime. Fair enough. 4K plus 1 could be prime. Yep, so give examples as it could be this, or 7, 5 or 7. True, right? So so for part A, you've shown an existence proof that it works for k equals 1. Now the next question is, can you show that it works for any k? Not necessarily, oh no, that doesn't necessarily work. Right, it's not all k. But can we show that k equals 1 is not just some aberration and it never works again, right? Because that would be silly. I don't know that you need to. That might be fine. Okay. If the product of primes, at least one of them, if P is a product of primes, then at least one of those prime factors must be 4k plus 3 for some integer k. Okay. Man. So P sub I must either be 4k plus 3 or 4k plus 1, right? So consider the possibility that every P sub I is 4k plus 1 for different k values, right? So you have k's 1 through n for all of your p's 1 through n. Makes sense, right? And now you got to say, based on that, what are you going to get for this stuff? Yes. Again, wanted to show that the product itself can't be prime. I mean, the product can't be prime because they themselves are prime numbers, and if you have the product of two primes, it becomes composite automatically. So that's kind of going in the wrong direction. So I think what you're going to end up showing is that by having a pure product of 4k plus 1, like any number of 4k plus 1s all strung together, then the product of that thing, it's not a prime because it can't be, but I think that the product of that thing is itself divisible by 4k plus 3. You're going to have to show that in some way. I'm not sure exactly why necessarily, but again, like in some way, shape, or form, there's going to be some k such that 4k plus 3 is going to divide whatever product you had here. Yeah, and that's fine. It's perfectly understandable if you don't necessarily know what you're going for. So it's saying that you have a product of primes, and each of those primes, by the previous question, all of them individually must either be 4k plus 1 or 4k plus 3 for some k integer, right? And then you assumed that every single piece of I is going to be 4k plus 1, and I love it. That's a great start to a proof. To say, okay, if all of them were 4k plus 1, then something wrong is going to happen. Or something that's perfectly acceptable, but then it turns out that it's also divisible by 4k plus 3. So you're trying to say, here, let's get this. Right, let's actually put this up here. Right? So, from the previous proof, right, we don't really need even positive, but whatever, it's fine. So it's not that the product is necessarily equal to 4k plus 3, but what it's saying is at least one of these prime numbers in here must be able to be expressed as 4k plus 3. Right, so our goal. At least one of P1, P2, ... Pn is expressible I don't like it. Yeah, okay. ABLE. For some k in the integers, right? And again, yeah, sure, it's positive, but we don't worry too much about that just because all prime numbers we're assuming are positive anyway. Right, so your claim that, or not your claim, your method is going to be express all piece of I equals 4k plus 1 case of I. Then 4k plus 3 is going to divide our original p, which, right, p is equal to the product as I goes from 1 to n of all p sub I primes. P is a terrible letter choice for that one, but it really just means product, right? A product of primes. Right, and just to remind ourselves, that is composite itself. Noises from below. All right. So I think this is sort of the strategy that you're going for, and that you should look at it as. So P is a product of primes. At least one of them needs to be expressed as pk plus, or 4k plus 3. All right, I agree with what you wrote at least. Again, that's the claim, so whatever. And your initialization of the proof, I think, is correct. Any p sub I greater than 4 needs to be written either as 4k plus 3 or 4k plus 1. And your initialization is that, let's assume that all of our p sub i's could be expressed as 4k plus 1. You're going to have a product. You're going to have a product of all of these things. We could express it as like the product notation, but that's going to get kind of nasty. Okay, so this is going to be probably a little weird, but let's try it. We'll go a couple of steps and then see if you can take it. So assume all p sub I are expressed as 4k sub I plus 1. So therefore we're going to get p is equal to 4k1 plus 1, 4k2 plus 1, times 4k sub n plus 1, like you wrote up top. Right? So this is all your work so far. Now, this being my channel and Simplex Pachinko, we are of course going to run through the 2 simplex here and figure out an answer that way. Okay, so we're going to have one number that is going to be the product of all of our k's. So this is going to be 4k sub I raised to the n. That's a terrible idea. Let's not do that. Here. This is going to be 4 to the n times the product of all k's. We're also going to, at the very, very end of this, have one that's just going to be a 1. Alright, the next one over. The number out front here is really, in this case, n choose n. The next one is going to be n choose n minus 1. So one of these numbers is not going to be the 4k term, it's going to be a 1. So this is going to be 4 to the n minus 1 times the product of I going from 1 to S. This is going to be terrible, but then you're going to hate the notation. It's fine. S minus 1. And I goes from S plus 1 to N. Really, what we mean is skip 1. There's probably a more eloquent, yeah, and elegant way to write that, but you know what? S is the particular term that you are skipping. So we are going to skip one of our 4k whatever terms. And so that's going to cause us to lose one of our 4s and also lose one of our k's. Yeah, this is again a terrible way of writing this. Because we could do it in any of n ways. There's definitely a better way to do this. So, Govin, for the first one. Well, I didn't say that. There still might be some way. Right, so the key here is going to be, is there a way to end up getting that plus 1 to end up becoming something that is instead 3 mod 4 instead of 1 mod 4. And right now I'm not seeing it. That's also a good question, right? Is it that it just can't be divided by 4q plus 3 because it's always just going to have a 1 at the end? Is there any way to get... Right, there's no way to get rid of 4s here. Our choose stuff gets rid of the denominators. I mean, it's possible. Anybody else have any ideas? Could show that it can't happen because it can't divide. One of them needs to be 4k plus 3 so that there is a possibility of a 3 at the end. Yeah, I think that's also possible, is that... Well, hang on. How did... Alright, cool. We're just gonna wait. Oi, if any of the followers are here, very, very sorry. Or if any of the subs are here. Very sorry. I should have seen that coming. The ad break counter on my monitor is just like... Gold was saying it earlier. It just doesn't make any sense. It doesn't do anything. Alright, 30 seconds. And we're back. Alright, sorry about that. Yeah, ad break just kind of snuck up on me because, as Dr. Gold was saying earlier, the counter is just not working. It is supposed to tell you, you know, hey, there's an ad break in 5 minutes. And I looked over and it said, there's an ad break in 5 minutes. And I said, cool. And by the time it hit about 3 minutes, it just jumped to ad. So, didn't give me the chance to, like, wind down and say, hey, let's, you know, everybody stand up and stretch and whatever. No, just decided that it was time. The bag with the big dollar sign on the outside. Yeah. I mean, honestly, I would, like, cut ads entirely out of specifically math nights. Or, like, say, I only want you to run ads when I want to run them. Which is more or less how it was before, but then it was starting to get insistent. And Twitch was also like, and we're only gonna do, like, I forget exactly. The ad share is significantly less if you yeah. It's like 30%, I think. If you let them control it, or if you do it within the appropriate amount of time, it's 55%, something like that. Which I was like, you know, it's kind of a bad deal not to at least attempt to do it. It's just, if they're going to run ads anyway, I might as well try to control them. Okay, so here's the thing, right? This never said that one of your pizza buys is necessarily going to be 4K plus 3. The claim is just that if there is going to be a product of primes, at least one of them needs to be expressible as 4K plus 3 rather than 4K plus 1. So the way that you have worded your statement from before the way you have worded your statement from before all prime numbers must be expressible either as 4K plus 1 or 4K plus 3. For some integer, and again, r being 1 or 3, gets the option of choosing which one's which. Now, it could be that we have a prime number which is only expressible as a series, or not series, but a product of 4K plus 1s in theory. And there's no way that you could then switch one such that one of yours that's expressible as 4K plus 1 could also be expressible as a different 4K plus 3. It's not possible, right? Because a number is either divisible by 4 or it has a particular modulo mod 4. So if let's contrive, right? So let's pick intentionally. Prime 1 is going to be 5. Prime 2 is going to be... Right, this is 4 plus 1. We want 4 times 2, 4 times 3 plus 1 is going to be 13. Right, times 4 is 17. And one more for good measure, right? Not 21, 27, 31. It's going to be 4 times... No, sorry. We're just doing plus 1. So, what's the next one after that? Posted a picture. Okay. Might as well take a look. So if you have that stuff, right, everything prior to the 1 is divisible by 4. So pull a 4 out, and then the rest of it is just integers by closure, right? Everything has to be an integer. So that all collapses to q, as you have here. And then you have 4q plus 1. Trying to remember if there's another way to end up with something else, because there was... Man, I'm gonna be frustrated with this now. So really my question, Govan, is gonna be, why is it not possible? Because again, if we contrive that all of the primes that we're multiplying together are just expressible as 4k plus 1, and that's it, like, there's no real issue. I'm going to say that the claim is false. Oh, 7 plus... Jeez. 4 times 7 is 28, plus 1 is 29. Right, so if we had this number, Right? 5 by 13 by 17 by 29. This is 32,045, which is 32,044 plus 1. And this is going to be 4 times 8,011 plus 1. So 4k plus 1. Right, there's nothing here. But why did you say that? Because that's not in the claim anywhere. Or rather, the claim is stating that at least one piece of I must be this, but... Okay, sorry. I think I just answered my own question. Right. We're showing that the claim is false. Because it is perfectly possible. Yes, the original claim is false. At least the one that you posted as part B. Oh, I don't know. This one right here. The one that says that if P is a product of primes, then at least one of them must be 4k plus 3. That's false. According to what we just did here. Oh, it's incomplete. Okay. Yeah, that matters. Okay. So are we still saying that P equals 4 is just a product of primes? Or are we saying like... Or Q is equal to a product of primes? Okay, so if P is a product of primes and can be expressed as 4Q plus 3... Big P is not itself prime. Okay, that matters. Thank you. So composite P is 4Q plus 3, where Q is the product of all of the individual primes itself. Then at least one of those piece of I's must be 4K plus 3. Okay. Yes. Alright, I agree. That's not it, right? This is not it. So we say not P, but capital P is equal to the product of these things, right? If we assumed that all P sub I were this, okay, both, sorry, both things. Okay, not that. So not Q is equal to, but also P is a product of primes given here, and it's for Q plus 3, where Q is some integer. Okay. I think we got it now. Oi. The contrivance here doesn't matter. Yeah, okay. So you're going to assume that it has to be equal to this. This means that we can take 4 out from everything. We end up with our 4 to the m minus 1 times the pi as I goes from 1 to n of k sub I plus all this other nonsense all the way down to we took the only 4 out. And then this leaves a sum of the individual k's plus 1. All this stuff is an integer. And so now P is expressible as for Q, let's call that an integer Q, shocking, for Q plus 1. And in this case, moduli are uniquely defined. So for Q1 plus 1 cannot be equal to 4Q2 plus 3. Oops. Right, so we can't possibly have moduli which are both 1 and 3. What is it? 1 mod 4 cannot be the same as 3 mod 4. Okay. So then with that in mind, right, you must have for p sub I plus 3. And like you did, right, if you put that in, then the last term ends up becoming 3 to the, I don't know, m. which can be equivalent to what mod 4? Right, so if we have 3 to a power, 3, 9, 27, 81, 243. Woohoo! 6, 7, 29. Come on, I should know these. This is going to be... Mod 4 is going to be -1, +1, -1, +1, -1, +1. Cool. So this could either be 1 or 3 mod 4. True, but you also want to say, like, at least 1, right? It doesn't have to be only one of them. So, showing that exactly one of them works is, again, it's sort of like what I was talking about with your original. It's saying, like, yeah, okay, it works for k equals 1, but, like, does it work further than that? And so you might want to revisit that and say, like, okay, for your first one, where you said... Nope. Alright, we're gonna bring this over too. Right, so if we're talking about this, now, as a math teacher, sure, just showing that it works at all is important. But saying, does it work ever again, might be equally as important for me. To say, like, you know, this is the actual, like, if I put on my mathematician hat, this is the more important question. Is k equals 1 just some aberration? Or does it work for some other k that's out there? Is there a pattern that exists beyond k equals 1? Tuvan throat singing. That's always fun. Duotonal singing is incredible. Especially done... It's especially coupled with Mongolian society is like one of the main places where culturally duotonal singing has become like popular. A lot of places in Europe just don't have anything even remotely similar. Mongolian mystery. Yeah, there you go. So again, I'd be interested to know if this exists anywhere else. You might want to look at this and say, okay, if... Ugh. Yeah, probably not. Since it says that every integer can be written in these forms. Yeah, that's fair. I just feel like going from here to here is a bit of a jump. I mean, not necessarily in logic, but in... Like, you were just talking about single examples, and then suddenly you're like, for every prime, it's going to be like this. So I don't know. Like I said, it seems like it's a little bit of a jump in scope, maybe. I guess, yeah. Every positive integer greater than 4 can be written in the form of one of the following. And therefore primes must be them as well. Again, 4k can't be prime, 4k plus 2 can't be prime. So you've eliminated all other possibilities. Okay. Yeah, never mind. I don't have a problem with it. Guess my you might want to state just before the end, right? That this means that primes must be part of the following, one of the two following sets, and we have two examples, 5 and 7, one of which belongs to each. It's probably fine. Since every integer can be written in this form and those can't be primed, then yeah, primes must fall within the other two. Yeah. And there's nothing you could do to eliminate one of them because you have an example for each. Okay. Yeah, okay. So for this one, I'm also just going further then and saying, like, no matter how many we end up having, where m is less than or equal to n, right, then you're going to have terms which show up in 4pi plus 3 such that you're actually going to have an odd number of those terms. Right, so this is 3 to the first, this is 3 to the third, and this is 3 to the fifth. Right, this is saying that m must be odd. Right, so there's an even more interesting structure there that exists. It's not just that we need at least one of them. We need to have an odd number, which ends up being less than n because, you know, you can't have more than the total number. Less than or equal to. That's a fun one. So I had actually done some work with a student who she'd actually done the majority of her work without any direction from me whatsoever, but occasionally came in because she was a part of the honors group and wanted to ask me a couple of questions. And so she was doing I'm not wearing the t-shirt for it today. She was actually asking about the magic square of squares problem. Where the sums of each of our rows and columns, right, are going to end up being equal to each other. And I've done this a few times on stream to kind of give somebody a leg up if they want to go for it. I'm not sure it's actually possible to solve this in any meaningful way, but she had a pretty brilliant idea. Yeah. So, as it turns out, we only have 8 equations for 9 unknowns. But we could at least figure out some of the, like, how reasonable would it be to find an answer? So the way that she started this out was she said, okay, if we simplify it and say, let's take, choose one. And basically pivot everything around it. So this is going to be a squared is equal to d squared. Hell. Sorry. A squared plus b squared plus c squared. It has to be equal to a squared plus d squared plus g squared. The choice of which one you do is without loss of generality, so take your pick. Any particular 2 equations that you want to select that have the same term in it, you can find them. This means that we've got b squared plus c squared is equal to d squared plus g squared, which also means that b squared minus d squared is going to be equal to g squared minus c squared. And then this is going to be equal to b minus d times b plus d is equal to g minus c times g plus c. And then if we invoke using some division here, we're going to get that it has to be true, right? It has to be true that the difference of squares must be divisible by multiple numbers, or multiple pairs. So if we kind of, either twist it or go back. We know that b squared minus d squared has to be, I'm the wrong way around. I always do this. Right? It must be true that g minus c needs to divide b squared minus d squared. G plus c needs to divide b squared plus d minus d squared. And likewise, if we go the other way around, these are equal to g squared minus c squared, and therefore b minus d and b plus d, and it's plus, it could have been the same way, must divide g squared minus c squared. Oops, square. Hey, Superbrain. It's the magic square of squares. One of my students was trying to prove that this was impossible, and she was one of the honors students as a part of our honors STEM honors society. It was give or take somewhere around 20 students in each year. Actually, it was separated out. Yeah, it was separated out by year. So we had a number of students who were in each thing. She was mostly playing around with it and got like, I don't know, 8 pages worth of notes or something like that. But it never quite got finished. It never quite made it all the way there. So she had a blast, like, working with some of her friends trying to figure this out. But yeah, it just never quite worked out correct. But then here's the other thing, right? Is that, well, all these other ones have to be the same as well. So that means that this one, there's 3 equations that have a squared in it, right? So this has to be equal to a squared plus e squared plus I squared. And not I as in imaginary numbers, just I as in a variable, right? So then that that also means that this is equal to e squared minus, plus I squared. And now you can pair these off in separate groups as well, meaning that this e squared minus I squared is, or no, sorry, e squared plus I squared has to be the same number as the other sums of squares. And then when you pair them off, we do get different differences of squares. But at the same time, now we have like multiple pairs of numbers that need to work out, and it gets really quite difficult. Holy grail of recreational math. Yeah, I mean, essentially. So, like, this is e squared minus b squared has to be equal to c squared minus I squared. And d squared minus e squared has to be equal to I squared minus g squared, right? These are different numbers from each other. We still get difference of squares values, but nonetheless, it ends up becoming really difficult to try and figure out how to make all of this work properly. So from here, we also went in kind of the same route that you did over here, Govan, where, surprisingly, right? She said if you... Where's my phone? It's on my phone. Hang on. Did I leave it downstairs? That'd be terrible. It's like the one time I actually need it, you know? And by need... Alright, where are we at for ad breaks? We still got 20 minutes. Alright. Really? Yeah, guess I left it downstairs plugged in. Alright, let's see. Huh. Alright, well, whatever. She said that let's choose that each of these differences of squares will have some particular modulus value mod 2. Right? So it's either even or odd. Okay, clearly. And that's fine. So that means that e squared minus b squared mod 2 is going to be equivalent to either 0 or 1. All right, no surprise there. So how does that work with each of them individually? So what about E and what about B? And the same with C and I. So she started chasing kind of a rabbit hole, which said, like, if e squared minus b squared mod 2 is equivalent to 0, then e squared mod 2 must be equal to b squared mod 2. Right? So they have to have the same parity, right? Whether they're both positive or both, or sorry, positive. Whether they're both even or both odd, it doesn't matter. One way or the other, it's going to work. So, cool. All right, and then similarly for C and I. Okay, then what about if E, no, hang on. I think she went individually. It's like if E P-adic numbers? Yeah, probably. Yeah, and I mean, this is one of those things where you're like, okay, look, hundreds of years of mathematicians have come before me. Clearly they know stuff about this that I don't. It'd be kind of cool if I just happened to find some little, like, thing to put a pry bar into and said, hey guys, what about this? And then somebody was able to become inspired and and do it. But all right, and then for parity of E and B, E squared mod 2 has to be equivalent to E mod 2. Right, so we could go in and say, okay, well, the parity of each of the individual values, if you just square it, it's going to end up being the same. And similarly, you could actually work that out doing a proof of going backwards and saying, okay, if it's even, if E is even, then E squared is even. If B is even, then B squared is even. And likewise, we can go the other way as well if we needed to. And same with odd, right? Anybody who's interested in that, right? It'll be a team. I want to, yeah, I think it's going to be the, I mean, honestly, it might be Yitang Zhang again. Because that man finds one little tiny way to make like an advance, which makes everybody else understand how to do it. Yeah, so I mentioned this, I think. So Tom Zhang actually taught my original proofs class, like that I was in sophomore year. He goes by Tom, but Zhang Yitang is his, you know, proper name. So he was working on the twin prime conjecture, and he ended up finding that if you set n to be some absurdly high number, then you were able to find an infinite number of twin primes that were at least n apart. For him, it was 70 million. He found like 70 million worked somehow. So there are an infinite number of twin primes that are at least 70 million apart. And then he wrote this paper on it, threw it out there in the world, and everybody was like, oh my god. A, why 70 million? B, we just like found an in. And currently, the n value yep, he was on number file back in 2013. Actually, I don't remember if he was doing a interview or if he was just they highlighted him. It's been so long since I watched that video. Twin prime conjecture, 70 million. I need the wiki on this. Yeah, people found like, oh, you know, a couple million and a few 100,000 and things like that, like very quickly. They ended up coming up with the values within a year, like down to, I want to say hundreds. Come on. Boo. Yeah, twin prime. There we go. Current. Prime gap. As of September 22, not quite. Yes, and close to 70 million, which, you know, hey, there we go, 246. The current value is 246, which is infinitely better than infinite. And is quite a lot better than 70 million. I don't know why he picked 70 million. Anyway, and then, it was like a few years ago, I saw his name in the paper again, and I'm like, no. No, come on. And he worked out another, like, another place to put a pry bar in, if you will, for Riemann hypothesis. Oh, come on. He said, when the paper was posted online a few days ago, this is 2 years ago, so 22, yeah. When the paper was posted online just a few days ago, many people who don't focus on mathematics didn't understand it. No kidding. Thinking that it was the Landau-Siegel zeros conjecture that was solved, and some even thought that it proved the Riemann hypothesis wrong. Actually, I don't have this ability. I only partially solve the Riemann hypothesis within a certain range. If I say I overturned Riemann hypothesis, few people would believe it. Commenter replies, what he's saying is that anybody with half a brain can do it in 5 seconds, because all you have to do is look at what you're working with. I mean, sort of. Jeebus, this comment section is a shit show. I mean, come on. It's Reddit. What did you expect? What do you mean unable to make comment? Ugh. End of file error. Secure connection failed. Now that is absolute nonsense. There we go. Okay, so so my student worked on the parity of e and e squared. Obviously, those are going to be the same, regardless of what they are. So you could say, okay, the parity of each of these things ends up being the same. The parity of e squared minus b squared has to be, or if it is the same, then we can go this particular route. If it is different, then we go the other way, right? So if e squared minus b squared mod 2 is equivalent to 1, then e and b mod 2 have to be different from each other. Hang on. It doesn't actually matter, again, which one is which. It's just that they're different. B. Right, so I think she was going for the p-adic eventually, because in this case she's saying, what did I just do? No, okay. Okay. If they're the same, either even or odd, again, if they're both even, nope. Whew. Okay, this creates two possibilities. E squared minus b squared mod 4. Right, could either be 0 or 2. And then, no, that's this one. Is either 1 or 3. Right, then we can go through all the possibilities. You know, could it's not exactly ideal, but there's probably a better way to do this, and so 0, 1, 2, 3. So mod 4. This is B up here. This is E over here. 0, 1, 2, and 3. We already said that they have to have the same parity. So if it's 0, it can't be 1 or 3. If it's 1, it can't be 0 or 2. If B is 2, we can't have 1 or 3, and if B is 3, we can't have E be 0 or 2 again. So again, this takes out some of the possibilities. And then you say, okay, if their difference in the squares was 0, mod 4, then right, so e squared minus b squared mod 4 is equivalent to 0, then e squared minus b squared is equal to 4k. And there's some stuff that goes on through there. Shit. Again? Righto. Well, I'm going to head out and do something here. So, water, snack, whatever. 3 minutes. Be right back. Just left the phone like upstairs, like on the edge of our bathroom sink. Like, you know, it's fine. Weird. Yeah, so my pictures. Math problems, that's not it. Honor seminar. Come on, what? No, it's the way beginning of this stuff. There it is. Hey, Butching. We're looking at a problem that one of my students was working on way back when, which was the magic square of squares problem. So she had come up with something to like help move it along, and I was trying to like coach her through a couple of processes. I don't think it by itself it never would have really got very far, and like right now it's just sitting stagnant. Like nobody's touched it in ages. God, she wrote in Arabic in here. I can't read that. Yeah, sure. Drop it in pens, or is it that one? The one that is in pens? Yeah, there was something else she wanted. She was saying if maybe if like g squared minus c squared mod 4 was equal to 1, then right, there was something we could say about it. Damn. This has been such a long time since I actually looked at this. Is it backwards from what I'm thinking? Is the other issue. Ah, that was it. Right? How would you get to any particular thing? So if we had like n mod 4 was 0, 1, 2, or 3, then what is n squared mod 4 for each of those values as well? This led me down a completely different rabbit hole, because I was like, well, what is like n to the k mod p or something like that, and we just went on like a whole crazy rant about how to do stuff. So this actually goes back to Govan. This goes back to your question this was something similar to what we did, where we said if we do n mod 4 and we get 0, 1, 2, or 3, then what's n squared going to be? So 0 is just going to be 0, right? Because you get 4k, you squared, it's 16k squared. It's still plus 0. You can't do anything with it. The 1 ends up having that 1 on the end, which when you square it, it just stays there. So that's also going to be 1. Our 2, the end bit, right? This is going to be 4k plus 2 parentheses squared. It's going to be 16k squared plus 8 doubled is 16k plus 4. Hey, look at that. All of it is divisible by 4, and the rest of it is integers. So that's it, right? It's going to be a 0. And then a 3, 4k plus 3, if we square it, ends up with 16k squared plus 24k plus 9. This ends up with plus 8 plus 1. So we end up having a 1 on the end. The 8, again, being divisible by 4. So if we do higher powers of, all of our individual n, the values that we plug in, what are we going to get for all of the landscapes of possibilities for all of the mods that we have? Mod whatever you want. So, like, what does mod 5 do? What does mod 6 do? What does mod 7 do? And then just keep going. So this ends up with mod 4. It all reduces down to either zeros or ones. And so when we look at whether we have a when we have something that said, again, this was g squared minus c squared, is going to have a modulus of either 0 or 1. Again, the moduli of the individual terms must be either same or different, which then means if they're same or different, they came from these potential values up top, mod 4, 0, 1, 2, or 3. And based on that, some of the possibilities eliminate themselves. So it becomes impossible for you to actually use certain ones. Okay. Sure. Downloads? Yeah, that'll work. All right. Okay. So the real part of all this stuff is just telling us that we're getting the... I could be wrong about this, but I mean... just the real part is telling us that we get our standard integral e to the mx dx is going to be e to the mx over m. Same thing here with e to the ax. We're just going to get, you know, that stuff divided by a. But then, right, what do we get for all of this other stuff? So since this is going to be two separate pieces, both a real and an imaginary part, all right, we're trying to combine all of this together. Okay, so we're using the real stuff to say this is what's going to happen with the complex stuff. And then we're going to determine whether or not that's actually true, or something similar, or based on part 3, I think it was, we're going to okay, interesting. So this is the integral of e to the ax cosine of bx dx, and the integral of e to the ax sine of bx dx, done kind of as one big thing. So rather than having to go through and say, let's do integration by parts multiple times through, what he said is, I'm assuming here, what they're assuming is they're saying, let's do this as two separate pieces. We're going to talk about the real stuff, and we're going to talk about the imaginary stuff. Only it's going to be all at once on this sheet of paper. So we're using the analog version of, well, it's just a complex number, so it's a constant, so that's going to still get dropped under, right? So, albeit complex, it's still a constant. And then here we're saying that all of this stuff is e to the I bx. So if you know Euler's identity, that's what this is. E to the I theta is cosine of theta plus I sine theta. It is a dead useful identity, and I love using it because it makes so much sense when you translate all of your cosine plus I sine stuff into this exponential form, because when you multiply things, their angles just get added together, and their moduli just multiply together, and when you raise stuff to a power, right, you're raising a power to a power, so they multiply. And then the moduli out front get raised to that power. So I just love the exponential form of this. And the proof that... Goodness. Do Not Move is the name of that track. Okay. It moved on by itself. Okay, so they take this and they say, all right, let's split it all up into its real and imaginary parts. All right, so e to the ax cosine of bx plus I times e to the ax sine of bx. Each individually can get the a plus bi constant. IB, right? Whatever you want to do. And then, in order to rationalize this, we need to multiply both top and bottom by a minus bi. which ends up with a squared plus b squared at the bottom. And then the top is decidedly less nice. A e to the ax cosine bx minus I times b e to the ax cosine of bx, okay, plus I times a e to the ax sine of bx. I see where this is going. I did look at it technically when I was saving it, but I got it. Okay, times, this is now going to be a negative, no, sorry, plus. This is going to be a negative I squared times b e to the ax sine of bx. This is a differential equation. This is a e to the ax cosine of bx. This is a minus negative 1, so that's a plus. b e ax sine of bx plus I times, parentheses, a e to the ax sine of bx. And actually, flip the sign. Make that a negative. Make that a negative. No, wait. No, I want the other one. Okay, we're good. Minus b e to the ax cosine. No. That doesn't quite work, does it? Alright, next question. Did I mess up somewhere? Come on now. Actually. One more part. Ah. Yeah, in theory. So, come on now. Please, computer. So, the way that I was looking at this is actually not quite what I'm seeing here. So my problem is actually right here. Because okay, I thought it was trying to prove that. It is. Okay. So I think that this is basically just a verification to show you that, yeah, actually it does work when you plug it in. Or when your intention is to do that. As much as I want to say, yeah, see, there's your problem, and then just walk away. No. No. The logic is right here. There's a slight problem with it. It's just that I slightly disagree with something. Maybe it's fine. Let's just check it real fast, right? So basically this is saying this is saying that e to the not 2 ax times the cosine of bx plus I sine bx divided by a plus ib is equal to that stuff. Right? Divided by a squared plus b squared. Which is going back the integral of this other thing with a complex argument. Okay. It's equal to all that. And then we just keep going through, keep going through, keep going through. Okay. Then from here, my issue is that this looks remarkably like TDX e to the AX cosine of BX, but it's not. right? The sign's off. I don't think it's actually a problem with anything your teacher said. It's probably just a problem with what I'm looking at. But if we reverse it, right? Specifically look at it as, what if it is a squared plus b squared on the bottom? Alright, if this was ddx of e to the ax sine bx right, how would that have been created? Trying to do di. I'm not sure I know what di is. That's alright. Alright, how would that have been allowed to produce this thing? Table for integration by parts. Yeah, gotcha. Okay, so that would be allowed to create this if, right, this makes a e to the ax sine of bx plus e to the ax b cosine bx. So what we actually see is an a. So we need to multiply by a over b here. Multiply by b over a here. How would that have been allowed? It isn't. Trying to think, like, is there some way that this could have shown up such that when it was integrated or when it was derived, it ended up showing this other thing? And it doesn't look like it, right? Because these are different from each other. So if they're different from each other, then it can't just be a simple constant multiplication going through. Grr. All right. Yeah, I mean, here I am thinking we're trying to prove integration by parts. That may not actually be it. I don't know what lipet is either. At least not by that name. Liate, yeah. So I have actually heard of that one. But, I mean, here's the thing, right? If we're trying to come up with... If we're trying to come up with whatever we got. Uh-huh. Yeah, yeah. I mean, like Punching said, I don't find it particularly reliable. It doesn't work in every single case. All I do is I say, what's easier to me? Do I want to take derivatives, or do I want to take integrals of each of these things? And integrals of exponentials are way easier to work out. Well, okay, exponentials don't matter that much, but like if it's exponential and trig, I definitely don't want to do exponential, or I definitely don't want to do integrals of all trig functions, right? Like I don't want to do integral of tangent. That's just disgusting. Why would I want to introduce natural logs and all this nastiness as much as possible? Yeah. So if we go by what's here, oh, okay, I get it. I get it. So they're not even saying... Really? Ugh. Okay. I just froze. Cool. Well, you know what? Deal with the fourth type to avoid even integration with parts, yeah. Yeah, I can't alt-tab or anything. Screwed. Alright. Well. I want to say there is actually a fix to this. But, oop. That just fixed it. I hit escape a bunch. Cool. Pro strat right there. I don't know what happened. It must have got, like, the stylus must have tripped something and been like, no, you want to work in this particular mode. And, like, nothing would change out of any particular mode. Yay. Okay. No, I think I got it now. So... yeah, okay, I got it. So all this is really doing is it's saying, let's take, right, the integral e to the a plus ib thing that we had up here. Let's split that into its constituent parts, which I had up there somewhere. It's fine. Which was the integral of e to the ax times e to the I bx dx, which is itself, let's just get rid of that, integral of e to the ax times the quantity cosine bx plus I sine bx dx, which is itself integral of e to the ax cosine bx dx plus I times the integral of e to the ax sine of bx dx. Alright, does everybody agree that that statement is true? That we can start with integral of e to the complex x dx and end up with these two separate integrals that have both e's and trig. So, especially Punchang, this is your question. So, capture that. Alright, so we take that e to the complex x dx, split it up into two parts, which end up being e to the ax cosine bx dx plus I times e to the ax sine of bx dx. Then, right, so sort of. It's less important to deal with just real and just imaginary. What we're saying is that the real part that belongs to this section has to now correspond to the real part that we established back here. And the complex, imaginary portion, that includes all this stuff with the I attached to it, and the a squared plus b squared on the bottom is just attached to all of it, has to therefore correspond with the other one as well. And since I is on both sides, you can divide it off. Or you could just say, the same as we do in a lot of these other problems. You know, if you have ax squared plus bx equals dx squared minus fx or something like that, right? This said that it must be true that a is equal to d and, did I say b? Yeah, b is equal to negative f. Right? It's not that we're just dealing with the real stuff. It's that we're now corresponding the two parts. So real to real, imaginary to imaginary, in the same way that back here we would do, you know, a quadratic equals a quadratic means that the coefficients must be identical on both sides. And in fact, right, if we want to go like this and go one further and say plus c, but then not add anything on the other side, this also says that c must be equal to 0. Yeah, you're basically doing a proof of it using complex numbers. Yeah, gotcha. Right, so then here it's that this is the real part of the integral of e to the a plus ib parentheses x dx plus the imaginary part I times the imaginary part of the same integral Right, so then all of this stuff has to be the real part. And then all this stuff must be the imaginary part. So with the real stuff, this is saying that integral e to the ax cosine of bx dx is equal to a e to the ax cosine of bx plus b e to the ax sine of bx all multiplied by 1 over a squared plus b squared. And therefore, integral of e to the ax sine of bx dx must be equal to 1 over a squared plus b squared times that stuff, a e to the ax sine of bx minus b e to the ax cosine of bx. Right, it's just all the stuff with a squared plus b squared as a constant out front, and then again everything that had an I, we're just saying these have to correspond to one another. You could also say that, you know, real equals real, imaginary equals imaginary. Sorry, that's the same thing. You could say real equals real, imaginary equals imaginary. Or you can say that we're looking for a real valued solution. So like we did in differential equations, we said, like, you know, there's going to be a constant that's out front of this stuff, and we're just going to let the constant be an imaginary number, which makes this thing real. Ta-da! It's a little hand wavy, but it works also. Alright, let me know if that helps any. Polar coordinates and differential equations. Woo! Okay. No. Ah, there we go. We also had a... No worries. Thank you. Variable force of magnitude f of x moves a body of mass m along the x-axis from x1 to x2. Net work done by the force in moving the body from x1 to x2 is work equals integral from x1 to x2 of f of x dx, which is going to be equal to the difference in the kinetic energies. Work done by the force equals the change in kinetic energy. Yep. So if a 2-ounce tennis ball was served at 160 feet per second, about 109 miles per hour, how much work was done on the ball to make it go this fast? Okay. We want feet per second, oddly enough. express weight in pounds. So that is 2/16 or 1/8. Yeah. This was Laz, I think. Maybe. Oh no, this was yours like a while ago. Okay, never mind. Yep. I didn't know it was actually completed. So you don't know what the function is to make that work, so it's not possible. Yeah. This was also the basis for an interesting question. All right, so that was solved. So this is net work, right? So the net amount of work that's being done. I imagine that this could be extended to say, like, here's the function for this particular thing. Now let's actually calculate what that work is based on just the function. And so you don't know what 1/2 mv squared is going to be. You don't know what it's... Yeah. Don't know what it's going to be in total. Right, and that also assumes that V1 is going to be 0. So you're starting from rest. So this was also another interesting question that was done on Numberphile a while ago, or it can help to inspire the answer to this particular question. So the question was, let's assume that a tree fell across the road. And it was unseen by two motorists. One was traveling at 50 miles an hour, and then when they see the tree, they're able to brake enough so that their front bumper just kisses the front of the trunk of the tree. Right, so x equals 0. The other car was going 100 miles an hour and started stopping at the exact same moment. Then what is the v final? What is the velocity at which the car that was traveling twice as fast is going to strike the tree? So there are a few different ways to work this one out. I'm pretty sure that this is the one that they used for figuring this out, and that is that both of these cars, if they're like of identical makes and models, which they kind of assumed they're the same car, it's just that this guy decides he's going to pass you, ends up getting to twice your speed when he's even with you, and then both of you notice that there's a tree in the middle of the road, so you slam on your brakes. Right? Given that everything is equal between the two cars, what's the final velocity at which the second car will hit the tree? Because again, if you're going 50 and you just kiss the bumper, right, then the other car is definitely going into the tree. Question is how fast. So the idea here was, okay, what is the work or network that's being done by this car to get from 50 miles an hour down to 0? Right, so V sub F is equal to 0 at x equals 0. So this was 1/2 m. Our V, we're going to make it, again, 50 miles an hour is going to be how many feet per second? Alright, 50 times 3600 divided by 5280. 34.09, with 09 being repeated. Right, so 100 miles an hour is going to be 68.18, with the 18 being repeated. It's just twice as much. Right, so 34.09 repeated squared is going to be equal to 1/2 m parentheses 68.18 repeated squared minus, nope, other way around, but same basic idea. V2, right? V2 is unknown. And so actually that's right, that the difference between 3409 and 0 is still going to be 3409, whether it's positive or negative. We're going to square it, so it doesn't matter what the sign is. This is going to be VF squared minus 68.18 repeated squared the 1/2 m's just go away. Alright, so VF squared is going to be equal to 68.18 repeated squared plus 34.09 repeated squared. Which is 5810, which when we square root it ends up, this is the answer they got to. Okay, VF is going to be 76.23 feet per second, which when we multiply by 5280 divide by 3600 ends up, oop, nope. Nah, I messed up. That was faster, so it can't be that. Other way around then. Oi. That didn't quite work. Really? Again? Urgh. Or do we just come back from an ad break and I just talk through the whole thing? Alright, I can no longer rely on my monitor. This is terrible. Yeah, this is a completely different problem. I was trying to work on the This was a problem that was done in number file. And they said so they'd said that the net work that was being done, the amount of the energy that was dissipated in either of the cars ends up being the same. So if you go from 50 miles an hour down to 0, then how fast is the other car, which started at 100 miles an hour, going when it definitely strikes the tree? A little bit dark, but you know. So I definitely messed up here. Yay. Oh, that's what it was. Okay, it's outside the parentheses. That's why. So this is a negative 34. Or negative 34.09 squared. Right. So this is supposed to be a negative there. Which means that that's a different number. Okay, that's better. Okay, so 68.1818, etc. Minus 34.09 squared. Okay, that's better. Yeah. Which again, multiply by 5280 for miles, divided by 3600 to get from seconds to hours, and we end up with a total velocity. This is feet per second. Was 59.047 feet per second, but again, miles per hour. Multiply by, oh, did I go the wrong way again? Jeez. Square root answer. We get that. Then we divide by 5280 and multiply by 3600. That doesn't sound right. All right, seriously. Unit analysis. Multiply by 1 mile per 5280. Yeah. Multiply by 3600 seconds over 1 hour. You get the seconds and feet go away. And then did I multiply those wrong then? Back in the original? 50 miles an hour. $52.80 over 3,600, because that's where you need that to be. So that should be a larger number. Man, alright. I'm fine, I promise. Yeah, I just went backwards for all of this. It's great. Alright, 73.3 repeated. And 100 is going to be twice that. So 146.6 repeated. So that's your 146.6 repeated minus 73.3 repeated squared. Again, that is not correct. Wait. No, okay. That's... This actually agrees with what I was looking at earlier. Okay, so I get a total of 127.02 feet per second, which, when you multiply by 3,600 divided by 5280 for the appropriate conversion, we get 86.6 miles per hour. So, this does actually work this time. Somebody might look at this and be like, how is that even possible? You should have been able to slow down by 50 miles an hour. So the other car should be going 50 when it hits the tree. Well, not exactly. So the problem with kinetic energy is that kinetic energy, as your speed increases, the kinetic energy increases as the square of that speed. So here in this case, if you're going twice as fast, you have 4 times as much energy. If we've dissipated 1 energy off of the original car, then the car that's going too fast is still going to have 3 of those energies left over. Right? Our speed is not linear here. So because the speed's not linear, this takes off like the smallest amount of those 4 energies, if you will, 4 energy units. It's only able to compensate for the top, in this case, about 14% of its speed, because it's going that fast. And if anybody wants to run the calculations and find out that I'm completely wrong, you know, feel free. But this is the same stuff that they got on number file. I could have sworn it was in the 70s, but no, I mean 86.6 also makes sense with the numbers in where they were. So this is one of those things where, like, when driver's ed teachers are like, hey, speed kills, they're actually right. Right? If you get into a comparable accident as somebody else, but they were going half as fast, there is 4 times more energy in your car. Which means that all of that energy's got to go somewhere, and if it goes to slowing your body down, it's going to be a bad day. All right. Oh, not that one. Curses. All right, so yeah, I think we're probably going to call it there for the night and head on over to, let's see, I think possibly tonight is an Astro Canuck kind of night, but we'll see who else is on just in case. Hey, Zach. Not that puzzled. Actually, right. Dr. Gold's on, so we're gonna head over to Dr. Gold's. Make sure to get in for any of those who's it's. Oh, okay. Yeah. Be sure to get in on any of the SAT math stuff that he might be doing. Looks like he's creating some questions using ChatGPT. So trying to create homework questions and then edit them, because goodness knows a lot of them do need editing. Do not trust ChatGPT ever. It will lie very confidently. All right. I will be back tomorrow. We're going to, Zach and Stuckey and I have discussed, we're going to do a quick wrap up to just say, here are some interesting things about differential equations, about what happened with the class this semester, and if anybody is interested in doing a an actual class here live with me, let me know what level, what subject, and we'll talk more about what we've got available. And I'm, me personally, right, I'm specialized pretty much in differential equations and in calculus and precalculus. So any of that stuff, might be interested in doing it. So let me know. And I'll be back tomorrow with Zach and Stuckey, and we'll talk about PDE sequel.